Ja. Ja. Kanske lite för högt, men det går nog bra. Ja. Ja. Ja.
Hello. Can you hear me here? Okay, welcome to the afternoon session. Now we are going to use the rest of the day for the materials technology session. I am Rolf Nyborg from IFE. I will be sharing this session together with Jack Ødegaard from SINTEF here. The program is up on the screen here. We have 6 presentations, and they are all very practical. Most of them are on corrosion and material aspects in flexible pipes, which is a very hot topic now, especially in Brazil, but also in other countries. And this is a of special interest both for Norway and Brazil, also because Norway and Brazil are the 2 largest users of flexible pipes in the world, both flexible risers and flexible pipelines. So we will have some very practical aspects on that. Yes. But before we start with the flexible pipes, we will start with the first presentation, and that is on the effect of H2S on the integrity of corrosion-resistant alloys for subsea service. And this will be presented by Daniel Blücher from SINTEF. So please, I think
Yes. Well, thank you very much, Rolf and Jack, for inviting me to have this talk. And I'd like to narrow it down a bit. So I'm going to present the susceptibility to hydrogen embrittlement for a copper nickel tin alloy C72900 exposed to H2S environment and under cathodic polarization in simulated seawater. So that's a more specific title, and this work has been done together with Professor Roy Johnsen at NTNU, the Norwegian Technical University, Torstein Lange at SINTEF, and Jim Stian Olsen from Aker Solutions. I'd like to present to you SINTEF NTNU expertise in corrosion. I will show you a brief film to highlight that, and some reference projects within H2S, hydrogen embrittlement, and hydrogen-induced stress corrosion. The background of this work for the copper alloy and the presentation of the test program, followed by the results and conclusions. So these are our colleagues working with corrosion and tribology. We are 13 people, and if I am now very lucky, I will have this film. Maybe I can PC there, notebook there. Oh. Try it again. Well, that didn't work. Well, why doesn't that work? I don't give up. I don't give up that easy. Where is the internet? Ligger där, ja. Så, jag tar ner den. Provar den igen. Där står någonting. Okej. Ja, det gjorde det. Hittar du internet här då? You find the internet. There it is. Ja. Ja. Mm. So, let me see if we can drive it directly from the internet then. So this is a short introduction of our corrosion laboratories, where the slow strain rig is loaded from Torsten Lange. It's to investigate for stress corrosion cracking. The samples are introduced into a jig for a load, and then introduced to a environment sitting in this rig. Environments especially with high H2S, high salinity, and aggressive. And after the exposures, we analyze for hydrogen content in the material. So Ann-Karin now, she's burning off hydrogen from the samples to see how much is has diffused into the substrate. And here we have post-test analysis of the samples. Do we have cracking? How is the substrate after exposure? Here we have a crack in a weld. And here we have a confocal microscope imaging a surface with topography through a layered imaging technique. Scanning over the surface. That's very good for pitting, for example. We also have tribology and tribocorrosion laboratory and climate chambers for paint and coating delamination with and without cathodic protection. Here Astrid, she's examining after exposure. This is our seawater laboratory where we take our water directly from the Atlantic Ocean. So we can, for example, what Nils Inge is doing here, he's loading the high temperature cathodic desponding rig with seawater. So that's a short overview of our laboratories. Let's see here. Yeah. After the exposures, we have access to advanced surface characterization. Also together with the Technical University. Yeah, you saw that in the film, so I skipped these. A couple of reference projects for H2S and hydrogen embrittlement and hydrogen-induced stress corrosion. We have a very good reputation in this field, not only together with the university but also with the companies in Norway and abroad. So a lot of research going on here. The background for this work is that copper alloys, they are widely used in the marine environment due to their corrosion resistant and anti-fouling properties. However, the drawback is limited strength and could show severe corrosion in polluted seawater. This specific copper alloy is called ToughMet. It's 50 nickel, 8 tin and the rest copper, combining high strength and anti-galling properties. Low friction coefficient. It's non-magnetic, easy to machine, and has acceptable corrosion resistance in selected environments. I will come to that. It's used in bushings and bearings for aircraft and heavy equipment with increased interest for using it in oil and gas industry. But the question we asked ourselves, will hydrogen influence the mechanical properties of this material? So what we did here, we took a forged unit and harvested samples for sulfide stress corrosion exposures according to NACE 15156-3 level 5 by the 4-point bend method, and in addition we did hydrogen stress cracking under cathodic polarization in simulated seawater with specimen under tensile load. And what we saw here, this is the microstructure of the material. What we saw here is that we have a yield strength of 787 megapascal. This is where the samples were harvested, about 40 millimeters into the sample. So there you see the samples from the rod. The test program for the sulfur-induced stress corrosion is according to level 550 degrees centigrade with 91,000 milligram per liter chloride, and we have a partial pressure of 7 bars H2S and 14 bars CO2. pH about 5, and we did 30 days according to the standard. So this is the machine samples where the upper side is facing outwards in the rod, facing out of the rod, and the inner surface here is facing into the rod. And this is the load applied to the sample and then immersed in the electrolyte in autoclaves. To check for hydrogen embrittlement, hydrogen-induced stress cracking, we did pre-charge the samples in a mixture of glycerol and phosphoric acid for 10 days at minus 1050 millivolt versus AgCl. So we polarized them and loaded them in this rig here, the proof ring for HISC testing. And here you see the electrolyte and the sample with the applied force. So what happened during the test? The material failed. It failed the level 5, and this is contradictory to some literature and to the material specification in the data sheet. It failed quite dramatically, not only severe corrosion, but also pitting and cracking, almost half of the thickness of the sample. So you can see here, we still have no broken samples. However, almost half of it was cracked and corrosion deposits on the surface. You actually see the corrosion here when you scrape off that deposit layer. So 3 millimeters into the sample, we had this cracking, and this is a blow up of the cracks, penetrating perpendicular to the applied stress, but also lower down in the material, sharp cracks below, not necessarily oriented in an orderly manner. And the cracking we saw is transgranular, so it's going through the grains. Here we see some more cracking of the material, pitting corrosion, and the deposited corrosion deposit the scale on top of the substrate. So the outcome of the sulfur-induced stress cracking was that severe corrosion, about 1.2 millimeters per year corresponding. And the yellow discoloring of the corroded surfaces indicate that copper is enriched in the surface and could be galvanically redeposited at cathodic spots, and this is a kind of selective corrosion. But what did the hydrogen embrittlement testing indicate? We see that we have in the charged samples about 14 ppm weight hydrogen content. You saw that before Ann-Karin, she was burning off from the samples. But without any charged, we have about the same. So there is no indication of hydrogen that influenced the fracture, the strength and ductility. So we have no indication of this. Here we have, after HSE testing, the upper two images are hydrogen charged, and the lower is not hydrogen charged, and there is no indication of brittle fracture on the fracture surface after exposure. This is a further evidence that we don't have HISC that influence this. So the samples loaded to about 90% of fracture strength, pre-charged, exposed for 30 days at room temperature in artificial seawater, showed no fracture or secondary surface cracks. And this makes us conclude that that this copper-based material is not suitable for that high amount of H2S according to level 5, contradicting literature, some literature and the data card, because we have severe granular cracking on the tension side and severe uniform plus pitting corrosion. However, the sample did not suffer from hydrogen-induced stress cracking. So I would like to thank Aker and NTNU for supporting this project, and thank you very much for your attention.
Okay, we have time for some questions or comments to Daniel. Everything crystal clear?
You can approach me in the coffee break and if you have any detailed questions. So.
Okay,
thank you.
Say thank you again to Daniel.
Så säg Gud. Så. Okej. Då har du agendan igen.
Okay, here is the agenda again, and the next presentation will be by Louis Pereira from Shell here in Brazil. And the presentation is entitled The Remaining Life Evaluation in Flexible Pipes, BGP and Solema Studies. And I will try to get this up.
And you have to press that button for 2-3 seconds. Hold it pressed for 2-3 seconds.
Hello?
Yeah.
Okay.
Okay, and for to pass, just... okay. Yeah. Ok, bom dia a todos. Boa tarde, né? Boa tarde a todos, good afternoon. My presentation today is about remaining lifetime of flexible. So I present some case studies that we are doing in Brazil. The subject is quite broad. Lifetime extension goes for polymers, corrosion, and many things in flexibles. I will dedicate a bit in Annulus corrosion today. But I will start giving a perspective of Brazil for lifetime extension, then some experience that Shell has, mainly in North Sea, and then some discussions about Annulus corrosion. So today in Brazil we are in an interesting time that we having a lot of old assets. That more than 40% of the assets has more than 25 years in operation. And we are also having the new generation of new assets coming mainly from pre-salt. But the number of old systems are significant, take into account that the average service life it's really 25 years. And before we finishing the production of the assets and before the commissioning, it's naturally expected that we go for a lifetime extension of the facilities to try to increase the recovery, the oil recovery in the field. And here in Brazil, we have a lifetime extension to be performed according to the NP resolution, the resolution 41, that covers the management of subsea systems, and also the internal procedures of the operator. This exercise of lifetime extension is basically a risk analysis of the pipe. We do the review of the role integrity and management plan that is in place. That also considers the evaluation of the design premises, evaluation of the operating history and the previous incidents that we may have. And we go in details with evaluation of failure modes and its mechanism. Sorry for the formatting. I think the presentation lost some formatting when transferring here. But about the Shell experience, I would say that Shell has a lot of experience in lifetime extension of flexibles, mainly in North Sea, in Shell UK and Shell Norway. Only in Shell UK we have already done about 80 flexible pipes assessment, lifetime extension for 80 flexible pipes. The internal shell guideline is very aligned with the NP resolution 41 that focus on risk assessment. And all operational flexibles that reached the end of design life have been life extended. So it's a common practice that you can go further with flexible pipes in fields. And some characteristics that we learned in Shell is the diversity and variability of failure modes in flexible pipes require a very, very demanding engineering assessment with a multidisciplinary approach. Naval engineers, polymers engineers, corrosion engineers, and that should work together to evaluate the different failure modes we have. Another point for lifetime extension is to collect the big data from operations with different types of measurements during service life, and how we store these and treat the data. And similar as well, how we recover our history of incidents, inspections, monitoring, maintenance, everything generates lots of data. So, jumping to one of the main, jumping for one of the main, would say, failure modes or concerns in a lifetime extension is the Annulus environment. Here is a picture of a flexible pipe in 3D and the 2D scheme from a technique paper with IFP. And you can see the Annulus. You can see the Annulus between the two polymeric layers. And this here is the bottom of the pipe with the fluids. The gas permeated to the Annulus. Here we have metals, the armor layers, and then the permeation can go to the sea, and this area here is the Annulus. So the Annulus is very challenging in the pipe. In the old projects, I would say that majority of them were designed for dry Annulus, and so it was assumed that there is no corrosion during service life. Today, it's different. Since the beginning, we already consider that the Annulus will be flooded sometime. Even if it's not flooded, we assume this in a conservative way. Because, again, the operation experience indicates that sometime during the service life, something happened, maybe during installation, or some water ingress from the end fittings, or any other thing that floods the Annulus. And the most used corrosion models are not good predictors for the pipe Annulus, nor SOC, and the corrosion models in other industry doesn't fit with the corrosion rates that we have here, because the flexible pipe has a unique characteristic with the confinement, which is the volume of electrolyte here, the surface area of the steel divided by the volume of electrolyte here is very, very low. So have a lot of steel to corrode and release iron to the environment. Arnie will talk more about this, yeah. Today there is no standards or procedures that you can use to simulate the Annulus environment in testing. So it's a lot of each operator doing some way, the supplier does in some way. And all interesting that our results are very consistent. So we could get a very low corrosion rates during the confinement, but the test setup is really a difficulty. We do differently, and it's something that we need to evaluate case by case. So to say that what Shell is doing here in Brazil to try to overcome these challenges in the Annulus, we do first the risk assessment and the mitigation plan, and the actions to evaluate the risks there. Also combine engineering assessment with, would say, advanced material testing and testing verification if necessary. For example, we do a evaluation layer by layer of the annulus, and how I would say the journey of the gas permeating to the annulus will affect or will impact the steels in the annulus, yeah, and we set up the tests according to this confinement, to these layers, and you need to discuss everything that is involved, polymer tapes, and everything that brings the complexity of the annulus should be assessed. So here are some points that you need to understand during this testing. If we are exposed to seawater, or if you have condensated water, it will change the way that we do testing. How we consider H2S consumption, but also CO2 consumption. We know that H2S consumption is very fast. A lot of papers published already that the models are very conservative, but the CO2 consumption, it's something that we are still discussing, mainly if you have a very high partial pressure of CO2, maybe it cannot be consumed totally as we have H2S consumption, but there are some chemistry in the CO2 that should take into account. Other things like presence of oxygen and cathodic protection. So a lot of complicated things that you should put in the testing, and you should overcome how to address all these things. And then we are doing advanced integrity management plan with technology, with research, improving inspections technologies. Just here some examples that we do, RUV, but you can associate how we detect wires with visual images from RUV, for example, maps, annulus venting. Also, some technology could be used as monitoring. And one thing that we are working here is the integrated monitoring. I want to show you a case, I would say, example for fatigue analysis, where basically we are collecting many would say environmental data of the FPSO. This is a Biju Perassalema, FPSO Fluminense. So we are trying to collect environmental data, wave, current, we are working on that. We put sensors in the vessel to measure the center of gravity, and then correlate the FPSO vessels with subsea response, with motion sensors in the risers, or I would say a riser response. We also can measure the wire strain directly in the pipe, Annulus monitoring to check the gases that we can see. And if we collect everything like in a cloud, we can put analytics behind it, like a magic toolbox, to give the fatigue analysis online, would say. Doesn't need to be daily or weekly, but like a way that we could easily access in the clouds and verify the results of fatigue. And then I would say that the benefits we are doing synchronizing the methodian data with riser dynamic response. Then we can compare with the premises in the project and see that we can improve life. We also are checking online Annulus gases that we use to update the SCN curves, or also to understand the corrosion in the Annulus, the termine Annulus. So we can put these in the intelligence here. And I would say that if you do this approach, we can follow the fatigue life in dashboards, and we really can reduce man hours with the team that will work to collect all data and do the assessments occasionally. So I believe you can use the digital solutions, we would say, to reduce costs for a lifetime extension. Here I just put one picture of the projects that we are doing with Fossil BC and UFRJ, just to have a taste that the magical box is true. So we can collect here is the gases in the Annulus. We can put in a dashboard. Here it's not everything updated yet. We are working this, but you can have here like the weather report updated, and then we need to add the other verifications that we need. So just to conclude, lifetime extension is an exercise that should be done case by case, pipe by pipe, with a dedicated risk assessment and mitigation plan. This is the baseline here and everywhere in different operators. Confinement of Annulus environment is key to decrease the corrosion risks. But the challenges are how we simulate the confinement in the laboratory testing. So to reach a ratio of surface of steel and electrolytes lower than 0.1 is very, very challenging in a cell. We believe that development of advanced material research and digital solutions, not static as I shown in the previously, but something dynamic that give all the calculations and the verification, can increase the safety of operation and really, really help the lifetime extension work. And the lifetime extension activities that we are doing today with these research and technology can be used as lessons learned to improve pipe integrity of the new systems that are coming. So it's something that you can apply. The question will be, what are the updates that we should do for the current integrity management plan? After we installed everything, it's very difficult. So since the beginning, we should be very clear which sensors we need to install, where, how we are doing the assessment. If you could put since, maybe when discussing the FPSO layout, so would facilitate the lifetime extension. And here is cutted, but well, I don't remember. It's something that technology really helps to rely with the current ANP resolution, resolution 41, that the operator needed to attend with ANP. Yeah, so that's all. Thanks.
Thank you, Larry. The floor is open for questions or comments.
After lunch, people are sleeping.
Yeah. Okay, if there are no more questions, then we say thank you to Larry. Yeah. Okay, the next presenter is Arne Dugstad from IFE in Norway, and he will talk about flexible Annulus chemistry, the relationship between pH, CO2, H2S, and dissolved corrosion products. And I think it's here. Please.
Thank you. Larry, he has already pinpointed that the Annulus chemistry is very challenging, but it's also very important because you need to understand what's going on in Annulus if you are going to predict any lifetime extension, because it's in Annulus it happens. Before I start with the technical part, I just have one slide from IFE, Institute for Energy Technology. We just call it IFE. It's an independent non-profit organization started in 1948. It was actually named Institute for Atomic Energy because we were and we are still running 2 small nuclear reactors. But it was decided in 1980 that Norway would never go for nuclear power. And then we changed name to Institute for Energy Technology, and we started to do oil and gas related work. And later we are doing now a lot on solar and wind and CCS, carbon capture and storage. I belong to this sector, petroleum technology, and I'm a corrosion man. And IFE have a large activity on these isotope laboratories, producing medicines and distribute radiopharmaceutical. And you see a nice picture here. That's a flexible. We called it a mid-scale test. It was finished this year. And some technicians put some nice eyes and mouth on this structure. So now it was called the Minion. And we have had school classes, and usually they forget everything about what I learned at IFE, but I think they remember this one. We have some activities here in Brazil. We have just started a large activity with Shell and 4Subsea. 4Subsea will have a speech later, but they are a Norwegian group, but I also have a small office in Brazil now. And together with UFRJ, IFE and SINTEF. And we have 2 PhDs in this project going to IFE, and the first one came yesterday. So I assume it was a little shock, going from 20, 30 degrees to 0 degrees, dark in the morning, dark in the evening, but we will see. And then we have another project with 4Subsea, where also Petrobras is part. And that's still ongoing, and we hope to start a new one next year. And we are open for more collaboration and joint projects, of course. That's part of the reason we are here. Laurie has already talked a little about how the flexibles is made. I assume not all of you are used to flexibles, so just spend a few more minutes. This is a bore. This is an inner liner, polymer, an outer liner, and in between these two liners, you have the annulus. And in the annulus, you have many different layers of armor wires. Some are pressure armor wires going spiral, and other are tension wires. And the problem arises when water diffuses into the annulus together with CO2 and H2S if present, and other hydrocarbons, and form a corrosive environment with CO2, with H2S, and also with other species. And this environment we call confined. And the situation becomes much more complicated, at least more complicated, if you have a damage in this outer sheet, that is either in air, in a splash zone, or in a sea. And then you get air with oxygen into the system, you get seawater into the system, you can have several damages, so you get some kind of a circulation in this annulus. And all that makes it very difficult to both understand and predict what is actually going on. And these are failure cases. Here you have got corrosion on the wires. Here you have got cracking on the wires. And this is what we fear. And this is what we have to predict. And we have to find methods to avoid it. It's some similarities, but also many differences between the annulus corrosion and more traditional pipeline corrosion. Similarities are that you have CO2 both places. You can have H2S. You have water. You have carbon steel. You have corrosion. And in both cases, you can get high corrosion rates if you have a reasonably high amount of CO2. But the difference is that this volume to surface ratio is so small in annulus. And all formed corrosion products cannot escape any place. Everything remains in annulus. In a pipeline, it goes to a separator. But here, it just builds up, and sooner or later, it has to precipitate and form solids. You cannot produce forever. For a while, you will produce, it will dissolve, you reach saturation, you reach supersaturation, it starts to precipitate, it forms protective layers on the steel. That's actually the reason why it survives, but you don't form it always. So that is very challenging. And if you have this, if you have H2S coming or diffusing also into annulus, then we come into this situation, will the H2S build up, or will it be consumed and kept at a low level? And if it builds up, cracking, of course, becomes a very big issue. I'll talk a little about that. And I have been working in oil and gas industry for research for more than 30 years. And we are usually very happy if we can say that the corrosion rate is less than 0.1 millimeter per year. But that would be a disaster in annulus. You need less than 0.01. So you actually need 10 times less corrosion rates than you would be happy with in the pipelines. And that requires very good protection and reliable protection by the corrosion product films, or whatever that cover the steel. Because in annulus you also have grease, you have tape layers, and that can also cover the steel. But it needs to be covered by something, either this grease or inhibitors that can be leached out of the soft material, or tape layers, or corrosion products. And then if it's coated by corrosion products, you have to be sure that it protects everything. This is cross-sections of the steel. And in this case, it protected this column, but not the rest. That corroded fast. And when you have partly protection, you get localized attack, pitting, whatever you call it. And it was mentioned Norsoc model. It was not good enough, Laurie told us. And this is what Norsoc model will predict in such annulus. The pH will increase due to accumulation of corrosion products. But when you reach a reasonably high pH, you still have 0.7 millimeter per year at 40 C at 1 bar CO2. So you need protection. You cannot rely on just non-protected corroding steel. It's a lot of reactions going on. You have iron reacting with the CO2 or carbonic acid in the solution, and then you produce iron ions and bicarb, and the pH goes up. When you have enough iron and bicarb, you start to precipitate iron carbonate, then pH goes down. And the same with H2S. When iron reacts with H2S, pH goes up because you form HS minus or S2 minus ions. And when you get precipitation, pH goes down. But it's one very important difference between iron carbonate and iron sulfide. Usually, SR is the saturation ratio. If the saturation ratio is 1, you have just reached the saturation level. But you can have supersaturated system. And for iron carbonate, you usually have a huge supersaturation, but not for iron sulfide. So while you can have supersaturation 1,000 times in a CO2 environment, it can just be close to 1 when you have H2S present. And since we have a confined environment, everything happens very quickly. So this is corrosion rate on this axis, and the amount of released corrosion product on this one, assuming no precipitation. And we can see that you reach very high concentration of dissolved corrosion products just after 1 day if you have a reasonably low startup corrosion rate. So this environment becomes supersaturated in hours, at least days. And when it's supersaturated, this just shows amount of corrosion product and how the pH increase when you get corrosion into the, or corrosion products into the system. And it's of course temperature dependent. But usually, at least in lab experiments, we see that we are in this region when it comes to corrosion product for the different temperatures. And that corresponds to a supersaturation of maybe 2, 3, 4, up to 1,000 or 800 times. And when you get this high supersaturation, then you start to precipitate a prototype layer. And if you have too little supersaturation, you will not form a dense corrosion product film on the steel. This is a cross-section of a steel and studied in microscope, so this is 10 micron. So you just get a report structure, no protection. And then you increase the supersaturation, and you start to precipitate iron carbonate. But in this case, it's too low. You precipitate in this porous film, but not close to the metal, where you actually need the protection. But in this case, the temperature is increased, and that changed the precipitation. And here you got iron carbonate close to the steel after some time, and you got protection. So it becomes so important, what is my corrosion product level? And it's too complicated now to go into detail, but it's a lot of issues related to this level and how to predict or maintain such a level in an annulus. But what happens then if we get H2S into a CO2-dominated annulus environment? Since iron sulfide is precipitating so easily, we have experienced that you are always close to this saturation when you get H2S into the system. And that is based on experience from a number of experiments, and it's publications stating that it's essentially instantaneous precipitation, and that indicates a supersaturation of 1. And that has large consequences, because the precipitation of iron sulfide will consume the H2S that comes into the system. And it's a direct relationship between iron and the amount of H2S in the environment. So it's impossible to have a high concentration of dissolved corrosion product and a high H2S content at at the same time. Either you have high amount of corrosion product and low H2S, or you can have it vice versa. But if it's controlled by CO2 corrosion, you will always have reasonably high amount of corrosion products. And that is called the consumption model or hypothesis or theory. And it's still debated, and it can be a little controversial. But at least in experiments, we see this all the time. H2S is consumed by the corrosion product. So it's not actually H2S that corrode the steel. It's H2S that react with already dissolved corrosion products. And that means that if you have a system, you have a certain amount of iron, which gives you a certain pH, and you are in this range of corrosion product, it's then not possible to have a higher H2S partial pressure than 0.01 or close to that. Without consumption, it could be several millibar. But when you have consumption, it's not possible. And that is very important when we talk about both lifetime extension and possibility for cracking of high-strength steel. So this is the last slide. It has been reported incidents where cracking failures have been related to H2S. But due to this H2S consumption, we can also question, is it really H2S? Or do we usually just blame H2S while we actually have other mechanisms? Because with some of these very extremely low H2S contents, we are at least far from people refer to the NACE test and NACE limits, and we are several order of magnitude lower than that in H2S. And then we have to ask the question, are there other mechanisms that can explain the failures? And we are deep into these type of projects now, trying to study these mechanisms in more detail. That finished my talk. Yes.
Okay, thank you, Arne. Are there any questions or comments to this presentation? Yes. Give you the microphone.
Thank you. Congratulations for the presentation. And I was wondering about the characterization of the different layers in the Annulus. Do you have evaluation or some comments about this issue? And the other would be the influence about the level, because if you have a condensation or seawater going through, you have a level of water, and if in these simulations you consider these effects of the part of the gas and the water.
In this presentation, I somewhat talked with what you say, large words. In reality, it's not a homogeneous environment. You have probably gradients from the inner liner to the outer liner. You have gradients in the vertical direction. And that makes the situation, of course, much more complicated. And you can have gas pockets and partly flooded systems. So it's still a lot of work to do to document that you actually consume, for instance, H2S all over. And I think it's no reason to assume that the Annulus is homogeneous, because you will produce, or CO2 H2S comes from the bore, have to go through all the different channels. It's a very complicated structure, and the flexibles are built with different type of organic layers to prevent wear. It's a lot of different layers. Some are more tight than other layers. So at the end, you need to take that into account to understand both failure cases and also the mechanisms that will control this H2S consumption model, and also control the level of corrosion products you can expect in Annulus. Was that the answer?
Okay, any other questions?
Congratulations on the good presentation. Lauro from Kongsberg. You say that are there other mechanisms that can explain the failures? So, based on experience, do you believe that it will be possible to, in a way, get a signature of the root cause of this failure? Whether if it's driven by CO2 or driven by H2S or a mix of everything?
I think it must be a mix. So I guess we talk about many different failure mechanisms depending on whether you have H2S or not in bore, whether fatigue life. So it's a very strong correlation between the mechanical properties of the steel, the stresses, and the environment. And of course that makes it very difficult to distinguish between what are the root cause of failures in different cases. So it's a little open answer.
Thank you.
And it's difficult to understand because the flexible or the Annulus is difficult due to all these channels, due to all this inhomogeneous distribution of both corroding species and corrosion products and gas and liquid mixed.
Hi. In the very beginning, you showed a few methods of preventing the corrosion, I think by tape, wax. Which one nowadays is the most effective?
Sorry, once more.
In the very beginning, you showed a slide with a few methods of prevention, like I think it was wax, tape.
That was it Lury's presentation?
No, I think you showed here. And then on how to prevent of attacking the piping. Which one of nowadays is the most used or which one is the most effective?
Prevention method? Or coating? I don't know so much about coating. Then you can ask maybe Svein Are Løtveit when he gives.
Okay, thank you.
Okay, it's a difficult issue.
This will actually be, I think it will be mentioned by some of the other presenters later today, so wait and see. Okay, any more? If not, then we say thank you again to Arne. Unless the morning session in flow assurance, all the speakers have been very good at keeping their time, and there has not been so much questions. So I suggest that we take a few minutes break, and we can start again here at in 7 minutes. 20 past.